I will do it again. So for those who were online, so we're going to start the EoR session. Miguel Morales kicking off with overview of the collaboration activities.
Which is, of course, a hopeless task. We'll go through and try and give a few little highlights of various things that people have been doing and things like that. There have been a lot of stuff that's been going on. So I am presuming, what do I have to do to get it to?
Here. That's one.
Am I allowed to? Okay.
Yeah.
So as always with, I mean, it's kind of the same theme year after year, right? Precision, precision, precision. And trying to do all the things right that allow you to go down to the kinds of depths that we need to do to try and detect the EoR power spectrum. And so I've kind of tried to group activities together, and you've heard about chunks of this in other people's talks and things like that. So, but a lot of work on RFI beams, vandalic corrections, pipeline advancements, and then I was going to spend a little bit more time talking about some recent science processing, but just kind of going through things. So one thing we did have a significant limit paper released. So this was last fall, since the last meeting. This was Mike Walensky. He talked about it at the last collaboration meeting, but that paper was published. The main thing about that was actually doing a much better job at RFI excision. And so if you're an aficionado of the two-dimensional power spectrum, what you really want to see above this line here is this speckle, which is noise-like. So these are from the observations that don't have any RFI detected in them. This is from ones which do have RFI, and you've allowed that to come through, and you can see that it's just completely full due to the spectral contamination of RFI. Interestingly enough, if you flag that with the most sensitive flaggers that we have, which are subthermal on individual visibilities, it gets better, but not terribly good. And so there's RFI that is still coming in. And so you have to flag out on a larger range than just when you can detect it. Now, particularly for the MWA and particularly at these frequencies, a lot of this appears to be airplane reflections. And so it's not that maybe surprising that during the 20 or 30 seconds when you can see the airplane, that there's tens of seconds to minutes on either side when you probably can't see the airplane, but of course it's still way too bright for an EoR observation. So you have to blank out much larger chunks of time and frequency in order to get beyond that. So anyway, he did do limits and things like that. And again, this is the 1D limits, and if you're not an aficionado, but this is the first time, so this particular one, we have the east-west polarization and the north-south polarization. And one of the things that had confused us for a long time is we were always getting better results down here on previous attempts in the north-south polarization. And this one they matched. And it's because most of the interference we see is in the east-west polarization because it's more sensitive at the southern horizon towards Perth. But when you filter really strongly, it improves rather dramatically in this polarization. So just a sense that things are doing, but we need to do better. Hence Jade's excellent talk yesterday, talking about all the things about trying to go even deeper. Moving on. These are measurements of MWA beams based on satellite. And so you can see that this is cycling through different beams. You can see that the measured MWA beams don't quite match the ideal beam. And so here is a heroic work to actually measure a set of what the beams actually are. And then you can do things about taking, as opposed to taking the perfect one, you can take the measured. Unfortunately, things are getting clipped off at the top. And then you can try deforming by adjusting the gains and things of individual dipoles within that to try and make it so that the beam pattern matches the measured beam pattern. Now, one of the interesting things that we've known for a long time and then carrying forward for the paper that is coming from this is that if you have faint sources in, and let me describe this as faint sources in your apparent sky, those will source spectral calibration errors. Now, it had been studied previously in the sense of catalog errors, i.e. you have a certain depth limit to which you can go, and then there are always fainter sources. And the PSF side lobes of those sources source then spectral errors when you try and fit your calibration at very low levels, but levels that we care about. Of course, these beam deformations provide a very similar effect, because if the beams change, then suddenly you see sources in different ways, even if they are in the catalog. They essentially are not at the brightnesses that you would expect. And so this is a set of simulations of showing what the calibration bleed is if you get your beams right, versus you simulate visibilities with the expected beam and then give yourself visibilities with the true beam. That difference throws calibration errors into the EoR window. And so trying to learn and figure out how to do that, and some papers coming on this. A bit of a theme talking about, because it's going to show up in different ways, is thinking about the MWAX upgrade and then the receiver upgrades, because that's such a theme here. This is an old little plot, so you can see the coarse bands here. Now, this is at a very small level, but one of the things we've known for a long time on the legacy system is the depths of these edges vary night to night due to the outside temperature, because amplifiers work better on cold nights, and those edges are nonlinear in the digital system, not the analog system. So we have a digital nonlinearity due to the, now there are a bunch of places that comes in. So you have the receiver, the analog, there's the 8-bit A to C, but then in the old system, after the 1.28 megahertz coarse channelization, there's a 5-bit requantization here. You then go into the correlator with the fine frequency channel. There's a 4-bit quantization before the X part of the correlator. And then as was identified, there was a 8-bit internal quantization in the polyphase filter bank and a bug, so that positive numbers and negative numbers were rounded differently. And that was a fun source there. And so trying to actually correct those. So there's been a lot of work developed in developing what was originally a 4-bit, a correction for the 4-bit quantization here, so a high bit Van Vleck correction. And that has now been ported into both PyUV data and Beerly, so you can just ask for your data on the old to be corrected for the 4-bit. There's been a fair amount of work trying to get this 8-bit one done, which requires simulations and stuff, but that is not live yet. And the student, unfortunately, who was working on that also graduated. So if somebody's really interested and wants to pick that up, talk to me for things. But what does that 4-bit correction, just the last one, do? So this is looking along the line of sight. So you have in the 2D space, this is a jackknife test showing it gets lower, but maybe it's better to think about this, which is a stripe vertically. Here, the foregrounds fall off, you get down to noise things, and then you see these coarse band lines, which come up. And when you do the 4-bit Van Vleck correction, those coarse band lines come down. That's also what's shown as the blue bars over there. Now, we're not doing science in this region anyway, but these lines are actually not narrow. They have wings which extend way into the areas in between. And so as you're able to knock these down, the hope is that that will open up regions between the lines in order to make those more noise dominated and allow us to get deeper. So there's been a lot of work towards that. And I'll come back to that to talk a little bit about variance on that later. Pipelines. So most of the EoR work, it falls into two different software pipes. And both of those have had significant and continuing evolution. So a bunch of the updates fall under that. So the first one is FHD Epsilon pipeline. That's primarily what my group and the US groups uses, plus Nicole Berry and her group in Sydney and things like that. And she caught up, so this is her slides, a couple of things, so we have 24 papers based on these pipelines with 1,200 citations and 13 of them student-led and things like that. This was originally written in IDL, and it's in the middle of a port to Python. We've gotten good resources for that. This is something showing that with the exception of a interpolation issue in the heel picks, which they are working on, they're getting close to having those two match. The testing is trying to get everything to match at all the various steps. And then there's some other things based on the US side for deconvolution, if you're interested. And one of the things that I'll throw up is that it actually turns out that PyFHD will be able to, for people who are thinking of arrays that do direct imaging, i.e. don't ever form visibilities, it'll take us about a year to get there, but it's able to deconvolve those as accurately as if you had the visibilities. And that's kind of an interesting thing for trying to actually show what kind of catalog work you could do by working off what's called a direct imaging array. So if people are interested on that, find me and we can talk. There is, all of this is an international sort of thing. It's open source. You can go find it on GitHub and the development. And there's also radioimaging.org, which shows things, with the exception that for reasons I do not understand, because it's a Squarespace site, it is blocked here on campus by the campus firewall. But your phone can get to there. And then on the Australian side, which is an even larger pipeline, so there's been a lot of progress and an enormous amount of work. So Beerly, which is the pre-processing, so again, flagging, involving the Van Vleck corrections, being able to get all these things out and stuff like that, dev. And then the other steps as you go down with hyperdrive and simulation and chips and things on the way to the power spectrum. But a few things that Kath sent me was talking about full end-to-end simulations, including catalogs, large sources, diffuse emissions, ionosphere, telescope and the beams like we saw earlier, and then actually going through the analysis. And there's so much information you can get from those end to end. And there's been a ton of recent papers and work going through and doing that, and a lot of lessons learned. There's then also been improvements, as there always are, on calibration, sky modelings, an enormous amount of work on quality control metrics and things like that, and some of the people who are doing that, and then updates to calibration software, again, Dev and Chris, and here showing calibration solutions. Are those phase or are those amplitude? Yes. And then Jack Line and the development of another simulator, Wooden, which is very precise and being used to make very nice, precise things and learn things about the EoR and test that we aren't getting signal loss in the analysis and various things. And there have been some nice papers about that. So moving along, I wanted to talk a little bit about some recent processing. Now, most of what this is, I'm going to, half the work, or maybe 2/3 of the work, I'm going to skip because Radima is just about to talk about it. And so I will let her talk about it, but this is But Kath mentioned some interesting things about trying to use, looking in the lower power spectrum spaces at some of the non-Gaussian tails and trying to figure out if there are ways to use that to identify certain types of foreground emission that may allow filtering to go down farther. But I also then wanted to highlight, partly because she's not getting a chance to do it because she graduated, Pixie Starr is a student with me, but also because this was a first run at the MWAX data, and I wanted to kind of walk through the MWAX correlator and what some of the advantages are and why we, from the EoR side, are so excited about the phase 3 upgrades. So just to remind you, this is the old system here with these various quantizations. With the MWAX upgrade, we got rid of both the 4-bit for the X and that internal misround. So this is now all held at 16, at floating point through there. But there is still the 5-bit quantization at this stage and the gaps between the bands. And of course, with the future SHAO and NI receivers, those both get upgraded in different combinations. But we're gonna, we got some, for Pixie's thesis, we got some director's time, thank you, Stephen, back in 21 to go do some EoR observations. I just want to kind of walk through a few of the things we've learned. So this is actually, so this is an auto correlation for one antenna to give you this idea of what the spectrum for one antenna looks like. This is raw coming off the correlator. And so you can see the overall spectrum, but you can also see these dips at the edge of every coarse band due to that. So then you can divide out the polyphase filter bank, because you know the taps, and because the nonlinearities are much smaller due to not having the 4-bit quantization stage, you get something that's kind of close. There's then a digital gain correction per channel, which gets it a little closer. And here you can start seeing that it's looking pretty good. You still get little spikes at the edges of the channels. That is still a nonlinear Van Vleck correction, but this is due to the 5-bit out of the receiver. We're going to trim those edges off with a few channels, and I'll come back to that. And then we're also going to fit these, it's hard to read small changes, so we're going to fit this with a low-order polynomial. I think it's a 3rd-order polynomial, so that we can see the finer spectral things. So this scale now changed, so you see we're at about a 2% gain calibration kind of scale here. Okay, it's wandering around, but one of the things you'll notice is this ripple. That's the cable reflection for this antenna. And so you can fit that reflection out, and we've trimmed those edge channels. And this is then, for the first time, because before these edge channels were so contaminated, we were not able to see, really convincingly determine what was intrinsic to the antenna and what was intrinsic to the digital system. So this is, for me, the first time that I'm seeing spectral structure that I'm pretty clear is actually from the antenna itself. And it's very repeatable. So this is 4 different pointings on the same antenna, and you see the same structure again and again and again. Now the sky is similar, but the side lobes change, and this is over 2 different nights. And so it's interesting to kind of see that, and this may also explain why, at least on the US side, we've used the autos as a bandpass calibration, and that's worked quite well. And I think it's because we're picking up this medium scale spectral structure as a part of the calibration through that term. All right. The other thing is new correlator, there are new features, and you need to bake down the analysis again. So one of the features of the new correlator is that the channels all moved, as opposed to starting at the bottom of the 1.28 megahertz. They are now centered on the 1.28 megahertz. And then, of course, all the Van Vleck corrections changed and things like that. So the idea is, what should we be trimming given the MWAX but the old receiver, and what can we be doing? Now, this is looking as a Fourier transform of frequency. So this is cutoff. It's 10 to the 14 in the lowest bin. But this is the first coarse band, the first harmonic, second harmonic, third. We call these the coarse band lines, and those are those same lines we'd seen before. But what is the difference between the blue and the yellow-orange? The blue is a simulation that has run through with flat spectrum sky sources. And what you'll notice is that there is a peak due to just the gaps in frequency. There's a frequency PSF. So we get a peak here that's just due to not having complete coverage. But this gap is larger when in the data. And that is at this point because the bandpass, the residual Van Vleck corrections are still there. And so we can try trimming farther. So if we trim, this is trimming one channel on the top end and two channels on the bottom at the 40 kilohertz level. If I trim two, you'll notice that as I go between these and I work my way down, you'll notice the model keeps climbing because the gaps get larger and larger, but we keep dropping in the data, which means that it is still dominated by those edge channel effects on there. So we're winning by trimming those farther. And so we are actually now trimming, before we couldn't disentangle those, but now we are trimming out 3 40 kilohertz channels on both sides, on both the top and bottom side for this analysis set. But that does give us quite a bit lower coarse band lines. So these are not all the same observation depth. So this is Berry 2019. This is the Walensky one from earlier in this year. And then this is Pixies. And what you'll notice is that these coarse band lines are progressive. This had the 4-bit Van Vleck on the old correlator. This is the new MWAX correlator. And that's getting fainter and as we go down. You'll also notice that the speckling is getting more prominent. That gets hopeful. And so if you go to a 1D power spectrum, this has not been published yet, but we'd like to push it forward to a publication. Now, again, if you're not an aficionado, but you'll notice that below the first coarse band line, we're getting consistent noise domination in the north-south polarization, which has always been our best one. And in fact, usually, sometimes in the east-west, though we think this still has some residual RFI sort of things. Now, this is not as deep an observation set because we didn't have as much actual observations, but this being noise dominated is very promising that if we can throw more observations at this from later seasons using the MWAX, that this will integrate down and become really a world challenging observations. And a third as much data, it's actually as deep as Mike's limit. And so there's hope that that is now starting to go down. Now, of course, we would love to not have these gaps. And so just to finish one last little thing. So the EoR, we've been talking a little bit in the collaboration things. I think the main thing to express is we are very excited about the SHAO receivers coming online. In a couple of, an MWAX. So part of it is we'd like to take the MWAX and find if there are good observations from the 23 season that we can use to integrate down or find any other ones to see if there's good stuff there, but that's very promising. But then looking forward to this, what is it that the EoR collaboration would love to have? And the wish list is more antennas is actually not what we want. I mean, someday, but going into the oversampling mode so we don't have those gaps is really the preferred thing. We, of course, need still compact coverage, but UV coverage is showing to still be very important. And so if you needed to bias, we would prefer more putting those new receivers for an oversampling mode on antennas which are on a more random UV configuration than the hex, but just putting that out there and stuff like that. But that's what and I'll show up one old picture because it's one of my favorites of folks helping build the previous upgrade to that. But anyway, I'm done. Are there questions? Okay.
Yes.
How do the systematics that are expressing themselves here for the MWA compared to systematics from EoR or live fire experiments? So are all the experiments hitting the same style of systematic, or are they all?
Oh, that's a yeah. So the question is whether or not the MWA systematics are similar to what's seen in other experiments or different than what's seen in other experiments. So it's mostly from the Hera experience I'll speak. It's actually quite different. So here it's really related to the spectral smoothness, and those gaps seem to be a real issue. There, let me go two different directions off of that, maybe three. The RFI environment for the MWA is quite good. I mean, we are still throwing more than half the data. When we go integrating down, but compared to other environments, it is still better. That's a big thing. The MWA's digital chunking is its own unique anti-feature. And so the other experiments don't have that. The MWA is much more stable. And that is a huge win. It is, I kind of forgot. So MWA, you kind of look at that and you look at a season's worth of data and go, ah, these two antennas aren't working. And maybe if you're unlucky, one dies during a 3-month period of time. But after that, it's dead. Other experiments, it looks like a different array night to night. And the calibration is wildly different night to night. MWA, you can, not a EoR precision, but for images, you can take calibration from 2 nights ago, apply it, it's fine. You'll get a little bit better if you redo it, but you know, it's 1 degree of phase difference or something like that. It's extraordinarily stable and repeatable in a way that others aren't. The last thing, which is really kind of wild, is that and this is kind of gone back and forth, but Johnny's group and Danny's group have been doing a lot of work with delay spectra, looking for coupling between antennas. So one of the problems that you have is that if you have radiation hit one antenna, scatter, go to another antenna, you now get a beating between this emission and this emission because it's time delayed, and that gives you spectral ripples between that. That is a huge issue in Hera. It was a huge issue in paper. I think the latest is we haven't definitively found it in the MWA. And that's really interesting. And there's theories as to why that is and stuff like that. Do we think it's probably still an issue that we have to worry about and things like that? But it seems to be a lot lower than the other instruments. Did I answer your question somewhere along the line? Yep.
There's one of those experiments.
Yep. Yeah. Probably not. One other thing that's actually come up, there was a really beautiful paper by one of Adrian Liu's students, Hannah Fronenberg is I think the name. It just came up, it just hit the archive a few weeks ago, which was looking with some care about cross-correlating with C+ observations. Including the foregrounds of carbon monoxide and various things on their end and 21 centimeters. But one of the things she was pointing out, which a lot of the literature hasn't done, is if you have foregrounds in one and foregrounds in the other and you cross-correlate, the foregrounds don't go away. They don't correlate, but they still add to your scatter.
There's a comment there on the cross correlation from Natasha. I don't know if you want to elaborate.
Hold on just a second. Let me finish where this is going. The interesting thing was for imaging style power spectra, which is what the MWA does in both of the in all the pipelines. What they showed then is that the foregrounds are important and the wedge is important, but you don't have to knock it down by 4 orders of magnitude. You only have to knock it down by 2 to 1%. We're not at 1% now, but we're close. And so, and that would give you something to where you could do a cross correlation, which might also help in a detection, but it also, even if you did a straight power spectrum, help actually show that you could do that. And I think the MWA is uniquely positioned to do that because of both the analysis and the UV coverage. I think no one else can do that measurement.
Okay.
Natasha, oh, sorry.
Yeah, so is it okay if you want to do it on chat?
Sure.
Because, yeah, time.
Natasha, send Slack or email me because I can't see the chat once I do that. Anyway, thank you.
Okay. Thanks very much, Miguel. So we will move on to our next speaker. And can you set up and share your screen, please?
Yes.
You can, okay, we can hear you and you have to share the screen.
Yes, I will just do that right now.
Yeah.
Which is a
closer.
yeah.
Okay. So Ridhima is going to tell us about the latest 21 centimeter results from Australian side of the collaboration. And I will give you 5 minutes warning, Ridhima. So all yours.
Right. Can you, thank you. Can you see my screen? Can you all see my screen? I'm not hearing anything. Hello? Can you hear me? Okay, okay. Okay. So, hi everyone. For those who don't know me, my name is Ridhima Nanhoki, and I'm a post.
Yeah, so
we can still.
We can't see your slides yet.
Oh, you can't see my slides?
No, not yet.
But
Oh,
it's on screen because he's written.
Yeah, she hasn't shared it.
Yeah, you haven't shared it yet.
It's only the screen.
Yeah.
okay, just give me a second.
Can you tell her that she's sharing the wrong screen?
You're sharing the wrong screen.
You're probably
Oh,
sharing the
I'm
wrong
sharing
screen.
the wrong screen.
Yeah.
As that, can you see my slide now?
No.
No, okay. So let me stop it and do it again. Share. And I'm sharing my. So I click on the screen. Okay, Keynote. Let me click Keynote. Okay.
Okay,
Can you
now I
stop
think.
this? Yeah, sorry.
Yes.
Okay, cool. Okay, thank you.
Yes.
Okay.
It's just
Yes, so
a bit of a lag, but hopefully we will see it soon.
It's still white.
oh, still white? It is saying you're sharing Keynote too. Is it
Not yet. It's still white.
yet? I'm sorry for that. I don't know. It's opening. Again, I'm sorry. Why is it? Oh yeah, it's coming white. I can see now.
Yeah, no.
It's coming like a
us.
white screen.
Yeah.
Let me do
Good.
something.
Um,
What was that? I don't know.
As someone who has to share way too much keynote, you might, you're probably presenting it to a screen. You can also choose to have it present in a window. In Keynote, you can go to View Options and say Present in a Window. And then when you hit play, it'll come up in a window and then you can share that. That might be helpful, but I don't, if you can also ignore me, but I just wanted to kind of, that has fixed problems for me in the past.
Yeah, but I have a screen. So when I click screen here, I don't have the option of window.
Okay.
I have in meeting window, I have screen.
Yeah.
I have option
Really?
screen.
You can just maybe share her screen with us and then she can navigate from there, not the exact, like that one.
Yeah, so this is working, so we can share the screen.
She can open the presentation.
Yeah, open the presentation on that particular screen if you can.
But it,
Yeah, if you can do that there, that should work.
screen, right? Oh, I think I know what's wrong. I think it's, okay, it's not allowed. It is asking me for preferences for WebEx. Yeah. Yes. Oh, I'm sorry, but I think it will just quit and reopen because it's denying preferences.
Yeah,
I will
that's fine.
just be back.
Yeah. Sorry about that.
Next presentation is in the folder.
Yeah.
If we needs more time, maybe we can swap into,
We can.
we can continue.
Right. But how do we, no, so.
She just logged out.
Yeah,
So
She just logged
it's
out.
not even in WebEx.
Right.
Ah,
Okay.
now she's
So,
back.
all right. So let's try this.
Okay, all good.
Yes.
Thank you. Yeah.
Yeah.
Yeah. Sorry about that. Yes.
Okay.
Okay.
Yeah, all good.
All good. All good.
Yes, so I'm sharing. Is it, yeah. Okay, so yeah, sorry everyone for the delay. So yeah, those who don't know me, yes, my name is Riddhima Nanhoki, and today I'm going to talk on the efforts from the Australian side. So we have been putting for the last 2 years, we have been putting efforts towards improving our upper limits. And this, to start off, is just a brief overview of the epoch of reionization, which is an epoch where our universe transitioned from being completely neutral to reionize. And we use a 21 centimeter hydrogen line to probe this epoch. And down below here, there's just an example of a simulation taken from Pritchard, which shows the time evolution of the fluctuation in the 21 centimeter brightness, and with a color bar showing the intensity, the evolution of the intensity of the 21 centimeter when it evolves through time, when you have absorption, which is a curve here. And we use observation from MWA. So during observation for EoR, targeted EoR, there were 3 fields that was targeted during this observation, which was based on trying to be away from bright sources like Hydra, Phonax, like other sources, but out of these free fields, we couldn't evade some of the bright sources, out of which was Phonax and Hydra A, which is EoR1 and EoR2 here, you could see. And here's just a map taken from MWA, which represents a field of view of MWA. And you could see the bright sources just in the primary lobe of MWA. So these fields are like analysis. Previous studies showed that they are dominated and actually contaminated our power spectrum result. And it showed that on EoR0 seems to be the best field. It's away from the galactic center, which is here. It's a cold patch. So all the observation, our analysis was done with observation targeted at EoR0. Now we have a lot of pipeline, like Miguel mentioned, across the globe, mostly in US and Australia, so which uses MWA data. And those calibration pipeline mostly differ in the software packages for calibration and power spectrum estimator. So for calibration, we have mainly the prominent one, which are being used now, FHD, RTS, hyperdrive, and redundant calibration. And mostly these, once we have the calibrated visibility, we can pass it through to construct our power spectrum. And this can be done based on either we have to go through the image space, or we can directly construct the power spectra from the visibilities. So from images, we have mostly the FHD and real-time system calibrated visibility used so far, and also now hyperdrive also have been included to include like use hyperdrive calibrated visibility to go through image plane. And then we use epsilon to construct the power spectra. And the other one is a visibility plane. So these two methods we use, which is the CHIPS, and CHIPS uses a graded visibility. And we have also redundant calibration, but this is very rarely used because we need a redundant array for that, because it uses a property of redundant baseline, where we have a baseline which has the same orientation and same length. And one of the pipeline which use redundant calibration with only phase 2 layout of MWA was Simple DS, which was done by Kulopanis. And now we have also all these efforts have shown we have challenges. The two main challenges we have been still facing is calibration errors and systematic. Miguel also pointed out very briefly those calibration errors, work done by Aman, which showed that we have uncertainty in the beam, and that can cause contamination in the power spectra. And at the same time, we have also uncertainties in our sky model. We have a model which has a mismodel. We don't know the exact flux, and also we don't incorporate all the sources. So we have caveats which can be exhibited in the power spectrum due to incomplete sky model. And at the same time, we have systematics, and systematics can manifest in various ways. One is instrumental errors at the receiver end itself. And we also have leakage across the dipole because they're two linear dipoles. So we are prone to instrumental leakage. And one of the most known systematics is RFI, even though we have flaggers in place, which work very good for all telescope, even MWA, but we still are not able to identify and mitigate RFI, which are buried under thermal noise, which are seen. Jade presented yesterday about how you can see even SINS is not able to actually detect some of the RFI, which are buried. So we'll use SINS and EoR flagger, the prominent ones. So we still need more effective flaggers to be able to identify those flags and RFI. And also we have contribution from the galactic plane and surrounding bright sources, because we're not able to model them as accurate as possible. So we can't mitigate them or subtract them. Also, even if we try to subtract them, they are very costly. Now, so now we have, this is just a schematic of the EoR pipelines that we use on the Australia side. I will go into details on the each steps in the coming slide, but mainly this the pipeline consists of 4 stages, which is a pre-processing stage, the calibration, and we have the power spectrum estimation and the validation step. And at each of these step, we try to apply data quality assessment so that we can detect systematic at each step from each of these outputs, so that as long as it goes through the pipeline, we try to mitigate most of the systematic dominated effects included maybe across time, frequency, and also in the observation as a whole. So starting, let's have a look at the observation. So we started with about 19,698 observation from the archive, which sum up to 656 hours of data. And all this data were high band data from 167 to 197 megahertz, spanning both phase 1 and phase 2 layout. And as I mentioned before, we use only observation with targeted at EoR 0 field. And all this observation was measured, were observed at different pointings. So the instrument was steered at 7 different pointings, and the altitude and azimuth of this pointing are listed in the table here. And coming to the pre-processing and flagging stages, so the pre-processing was done by Bearly, which is an improvement to the existing software Cotter, and Bearly was developed by Dave, which incorporate many other features which didn't exist before. And so it tries to identify quality issues and discard observation. These quality issues include errors in the beamformer communication, and if we have recorded events from the MNC system, and also presence of 2 or more dead dipoles, because we don't have a system in place to account for that. And we also discarded observation which has high level of ionospheric activity. And previous studies found that if you have a rotation measure greater than 5, and that's ionospheric, the matrix is greater than 5, we discarded that. And we also apply EoR and SINS flagger to identify and mitigate R5. And
Remember, you have got 5 minutes.
After we average the visibilities across frequency and time, and we also use autocorrelation to identify misbehaving antennas, are shown in this figure here. You can see we have some antennas which can be seen here in the RMS plot, which is across antenna number, so we discarded them. And in addition, we also discarded observation based on the flagging occupancy from EoR flagger and also SINS flagger. And then we calibrated our data using the Hyperdrive software, which was developed by Chris Jordan. And we use a Lobes catalog, which was a survey targeted mainly EoR field 0. And we use the beam, FFE beam, and the number of iteration we used was 300, and number of sources was 8,000. And in order to exclude galactic emission, we use a baseline cutoff less than, so all the baseline greater than 30 lambda were included in the calibration. And also we use a convergence value that is obtained from the calibration to identify if we need to discard that particular observation, if the convergence was greater or if the particular observation didn't converge at all. We also did an inspection on the amplitude and phases of the calibration solution to see any misbehaving antennas. And you could see this figure of an improvement of RTS, of hyperdrive over RTS, where the galactic center is more greater in amplitude rather than RTS, and can be seen even in the difference image. When you have the side lobes is more prominent in RTS of the sources than hyperdrive. So it's clearly an improvement. Hyperdrive is clearly an improvement over RTS. And then moving on to foreground subtraction, we again use hyperdrive for foreground subtraction. And we did a direct subtraction of 4,000 brightest sources. And we, on top of standard subtraction, we correct for the phase offset due to ionospheric activity. And that proved to be a improvement in observation, because if we do direct subtraction, we face with under subtraction and over subtraction of sources, which can be seen clearly here in this image. Here. This is an improvement where we did a difference image where we don't apply the offset correction, and we can see that there is clearly the one this is highlighted is a stronger source in the field of view, which is and then you could see with a ionospheric correction, we were able to extract more flux. And with also coming to the quality assessment, we did using the delay transform visibilities, we actually derive 4 matrix, and also we use the image statistic to derive another 4 matrix, and based on those 8 matrix together, we evaluated threshold to discard observation which are systematic dominated. And also because we use both phase 1 and phase 2 layout for this analysis, we found that when we did those quality assessment, there was a discrepancy in those amplitude of this matrix. So we computed this threshold for this 8 different matrix separately for phase 1 and phase 2. However, we saw that this is an example of phase 1 when we did a marginal plot of this 8 matrix. We could see that and the color bar represent the different pointings. And we can see that pointing -3 is very prominent. It is very high in amplitude. And this is because the galactic center is in the second side lobe. Here it's still like close to the side lobe of the main beam of MWA. So it is contaminating all the observations. So we discarded all observation from -0.3. Yep.
2 more minutes.
Okay. Yep. So we got rid of all observation from -0.3, and based on the threshold that we use, here is an illustration of how many observations were discarded, and in total, 52% of data was discarded, implying that more than half of the data we started off were discarded. Now using the clean data, so-called clean data, we constructed our power spectrum, and this is a representation of a 1D power spectrum, and which is in magenta here, and we compared it with 2 other plot at this particular redshift, which is Z is equal to 6.5, and we can see this is an improvement over existing upper limit at K is equal to 0.18. And so these are the 2 limits that we found is we did an improvement, which is at redshift 6.5. And this is the best MWA has ever produced so far. We also derive limits at redshift 6.8 and 7, because we have instruments such as HERA, which produce limits at Redshift 7. And with the help of Dr. Yushan from the University of Melbourne, he helped us to do the cosmological inference from the limits that we have. And he actually made a very nice plot here comparing limits that existed from different instruments. And we can see that now MWA has started to exclude model, which earlier limits didn't. However, the limit still, Hera is still the best. As you can see here, because of the redshift it is already like MWA is already excluding the limit which Hera has. But so far we have produced, MWA has started to exclude model, and we are looking forward to improve the result. And yes, so in improving the result now, there's still a lot of work to be done to the pipeline. We can make improvement. And also there's a validation test that needs to be done. Like I mentioned before, we still have to do, and the work is in progress. We have to do a jackknife test or bootstrapping. And there's already a paper in place for the systematic mitigation. And also Jack Klein has already papers in place which shows that we don't have signal loss from a use of from calibration. And also we have been working in validating our pipeline against other pipelines such as FHD. And we have been, especially Dave has been working on implementing Van Velde correction. And Kat has been working on trying to use a kernel density function to measure the spatial fluctuation in the EoR power spectrum to better constrain the foregrounds. And if we can, and thus better remove them, and we can get improved power spectrum limit. And this work is done by a combination of people from Australia, and this is the team. Thank you.
Thanks, Rudima. So we have got time for a very quick question. If anyone has nothing from online, but if there is anyone has a quick question from the room, we can take that now. Okay, so I don't see any hands. So, oh yeah, quick one, Freya. Okay.
Thank you for the really interesting presentation, Ritima. I was just curious, is there any plan to use the EoR1 and EoR2 fields for future observations?
For now, we don't have any plans to use it because EoR1 has Phonax A like a dominating source in there. So we need a better foreground model for Phonax A to do the foreground subtraction. That's the reason, but we have in place, we have been thinking of, because we need data, if you have more data, we'll be able to get better limit. So at some point, we'll also include EoR1 and see how well it works with the pipeline.
Okay, thank you.
Thanks, Ridhima. So we will move on to the last presentation before the lunch, and that is by Chris Finley on trajectory-based RFI subtraction and calibration. Over to you.
Excellent. I think so. How's that? Great. All right. Thank you very much. Do we have a clicker? Or...
No.
Okay.
Up to go with that one.
Yeah.
So that-
Okay. Cool. All right. No problem. Yeah. Sorry, I'll just have to stand here because I got a few little transitions just to help with it, but I guess that helps because I also don't have a pointer, so the transitions help for that. So yes, my name is Chris Finlay. I'm a PhD student at the University of Geneva. I won't be talking about EoR, but hopefully my methods can help with that, right? And I'll try and be as quick as possible because I know I'm keeping you for lunch. So yeah, So trajectory-based RFI subtraction and calibration. It's a bit of a mouthful, so we've just called it Tabasco for short. Oh, not that one. Just click. Okay, cool. Just click in the middle. Cool. Yeah, so just a little bit of motivation for radio frequency interference, why we want to be dealing with it. So I've been mainly working on Meerkat, so this is going to be a little bit more Meerkat specific. But about 30% of the Meerkat L-band is contaminated by RFI. So we can see here, here's a nice little plot of the fraction of the time that's flagged across the frequency band, the L-band specifically. And if we have a little look, you know, it's got nice little labels here. Most of this stuff is satellites. A lot is GPS satellites. We've got some airplanes, and we've also got some GSM towers. And what's nice about all of these sources is that these are reasonably predictable, right? We know where they are going. After an observation, we know where they have been. You know, a cell phone tower isn't moving magically. And as we saw from Jade's talk, a plane moves in a nice straight line. And just to sort of quantify the cost of actually just flagging the RFI out is we're losing about a third of the data, right? So for Meerkat, it was about $330 million for that. So it's about $100 million that we're losing to RFI. So it's an important problem to try and solve. So an interesting feature of RFI is that your level of RFI contamination is very baseline dependent. All right, so RFI is stronger on shorter baselines than it is compared to longer baselines. So this plot right here is just showing sort of essentially the fraction of time that's flagged versus the baseline length. And this is because of fringe washing, because the RFI sources are non-sidereal, right? They're not moving with the sky. And we're not taking data at a high enough time resolution, usually when we're doing sort of an imaging observation or something like that, which is on the order of a couple seconds per data point. So Tabasco. So what we're looking to do with Tabasco is to try and replace RFI flagging with RFI subtraction, right? So the point of this is to try and recover astronomical visibilities. And what we want to do with it is we want to have it fit into the current data reduction workflow, right? So you've got 1GC, which is essentially like transfer calibration. So look at a known source, try and characterize your instrument, and that's, you know, apply those calibration solutions to your target. And then 2GC, which is where you're looking at your target and you've now essentially used your sort of initial estimate from transfer calibration to further calibrate your target observation. And the ideas behind Tabasco to achieve this goal is to use the trajectories of RFI sources to help estimate their visibility contribution, and to estimate antenna gains by using prior information. So if we're in a contaminated channel, you typically can't just directly calibrate in that channel, but you could use information from a neighboring channel that isn't contaminated. Right? And we also expect some baseline dependent smoothness in the astronomical visibilities themselves. So a short baseline will have slowly varying visibilities, and a longer baseline, they'll vary more quickly. So then the question also becomes, how do we distinguish between RFI and astronomical signal, right? So as I said before, RFI has non-sidereal movement, right? So what this means, it doesn't move with the stars, right? And it therefore has a high relative time variability. So the phases are changing rapidly. And it affects all baselines differently because of their orientation, right, and their length. So just in this plot to the left-hand side, we can see in blue just the RFI signal that we expect on its own. In green is the combined signal, and we're trying to essentially separate this smooth component, which is the orange part, from the blue part. So to this end, it's pretty hard to just apply this and figure out whether we're doing a good job directly just in real data. So we've developed some simulations for RFI. So we've put together a nice simulator that is available on GitHub. And for this, we've got satellite and ground-based sources of RFI that you can include. We do include like a correlator averaging so that we get that correct fringe loss for our RFI sources. We can include time and direction dependent gains, and all of it's implemented in JAX, which essentially means we can run it on GPUs, and it's with DASK, so we can also use multiple GPUs. So starting to do bigger simulations. So part of how we do the simulations and also the forward model for our method is using the RIME, the radio interferometry measurement equation. So it looks like this, but it can be easily broken down. Right in the middle, we've got the brightness matrix, which are essentially your Stokes parameters. And this will work for astronomical sources as well as RFI sources. Then we've got our phase delay terms, which is essentially just our geometric delay. So we've got assuming plane waves for a far field source, and then we can have curved wavefronts, spherical wavefronts for an RFI source that's in the near field. We've got our direction-dependent effects, so that's things like your primary beam, maybe also ionosphere and things like that, depending on your array configuration. And we've got our direction-independent effects, so that's things like your bandpass. Right? So all of that is in a standard simulation apart from the curved wavefront. So whenever you're doing visibility simulations for astronomical signal, you have these parts. The extra part that's really required for RFI simulation is this correlator averaging, so that you end up with this reduced power on the longer baselines. And that's essentially like what's happening in your correlator. And from this, we get our visibility. So Tabascal 1 is essentially like, okay, we're wanting to do 1 GC. So this is looking at a calibrator, right, and characterizing our instrument. So here we want to jointly estimate the RFI signal, its trajectory, and the antenna gains, right? We're trying to characterize our instrument, and we also don't exactly know what's going on with the RFI, but we know what's happening with our astronomical source. And we put this all together in a Bayesian model to reliably estimate these parameter errors as well. So this is what the model looks like. So first we've got our RFI signal, and we have this, we're estimating parameter of every single time step on every single antenna, right? And this is like an apparent sky essentially, but it's on each antenna. Then we've got our RFI trajectory. So, you know, that could just be the straight line of an airplane or the trajectory of a satellite. Then we've got our complex antenna gains. And all of this goes into a forward model. And we have a likelihood, which, because this is all simulating in the visibilities, just uncorrelated Gaussian noise. Right? So some of the results from this, here we've got, in the top panel, we've got the visibility amplitude from the RFI and astronomical. So RFI is in blue and astronomical signal is in red. And what was interesting with this is, you know, we assumed that we've got an RFI source that is very close to our calibrator. And we were actually then able to essentially calibrate off the satellite as well. This is in simulation. So what we can see here is that when we've got reduced power from the RFI, that's gone quick. We've got a larger spread in our gain phases, and we have a reduced spread when we have got a stronger RFI signal. And that's summarized in this plot just here. So Tabascal 2 is when we're now on a target observation. So we use our prior estimates from the first run on a calibration observation, and we now want to estimate our astronomical visibilities. So to do this, we need to introduce some prior information, and that is this smoothness that we have in the astronomical visibilities. So just as an example here on the top, we've got a shorter baseline, and you see over time it's very smooth. And then we've got a longer baseline that is much more time variable. So we can encode this in the covariance for a Gaussian process and use that as a prior. And the results from this is, so this is single frequency imaging. We end up with about 90% of the data flagged here. And just through traditional flagging versus using Tabasco, you end up with about 3 times lower image noise, right? Which in fact is slightly lower than the ideal case of just sort of traditional calibration with no RFI contamination. But this is because we're adding prior information, right? So traditionally, you wouldn't add any prior information, you're just doing a maximum likelihood estimate. So you get sort of a denoising effect in essence. So when we do point source recovery on this as well, so in orange, we've got the result from flagging. So we see that we're underestimating, and we've got a much wider spread. So this is the true flux along the bottom axis, and then on the y-axis, we've got the error, right? So we know what we put in, and we calculate the error of what we get out after using PyBDSF. And we can see that for Tabasco, which is the green, versus the ideal case, as in uncontaminated data, which is red, we end up right on top of it. We're recovering our signal of interest properly. So also getting it slightly EoR related, so on power spectrum recovery, it's very interesting there because most of the stuff that's getting flagged is these short baselines, which is your large scale structure. So we can really get a large improvement there. And here we're just flicking between using Tabasco on, this is an 80 hours equivalent noise, but an 8-hour observation. So this is Meerkat L-band, so very low redshift, and only like a 1.2 degree field of view, so you aren't able to reduce the cosmic variance too much, but we do get a huge improvement. So also, because it's a full Bayesian model, we would also like to do uncertainty estimation from that. All the previous results is just like getting the maximum a posteriori, the map estimate, right? So maximum likelihood, but a Bayesian setting. But we're now dealing with millions of parameters. This is really hard to do. You're not going to do it with MCMC in your lifetime. Right? So what we're trying to do here is sample the posterior covariance, and we do this with an interesting method that you can come and talk to me about. But because we've got everything in an autodiff framework and we can do some implicit definitions, we can essentially sample from our posterior distribution, assuming Gaussianity, in a scalable way. And we do this just only needing to sample from our prior and from our noise, and then we can just plug it into these equations here and get out samples from our posterior. Right? And you can choose how accurate you want these samples to be and how many samples you want. So you've got this nice accuracy performance trade-off. So just as far as what we're looking into the future for here is we have submitted a past proposal. So this is specifically to improve the scalability so up to supercomputers or tier 0 supercomputers. So just loads of GPUs, many nodes, right? And part of this will be developing a test and benchmarking suite and maybe get into some nice imaging things. Something we're also working towards is this space sustainability. And with that, we'll be testing the limits of Tabasco and really trying to work towards a proper space sustainability rating for radio, right? So they've got it very well for optical, but they could do with a bit for the radio side. So just in conclusion, so Tabasco can be used to subtract RFI and therefore recover the astronomical visibilities. And at some greater expense, we can deal with stronger sources of RFI, multiple RFI sources, which are going to be a requirement for satellite constellations. And we can also do uncertainty estimates with this accuracy speed trade-off. And yeah, some ongoing work that we have now, just testing the limits and trying to get onto testing on some real data. Thank you very much.
We have time for a couple of questions.
You have to repeat the questions.
Okay.
You can ask the question and then we'll get close to it.
Yeah.
So, what I shouldn't think about this is maybe just your comments on what happens as you go wider field of view, because
Okay.
visibility is very steady near your field of view center. It's fringe stop. Where, so in RFI, how much of this due to it tracking versus, source, which is very far off your fringe stop, and will also, your stop will start fringing, and now those start looking a little similar to each other. I'm sure you've thought about how well does this separate those, or the field of view limits, things like that.
I'd like to briefly repeat it.
Yeah, I'm going to try to summarize your question, both for myself to answer it, to clarify, and for those online. So is it specifically about trying to distinguish between astronomical sources that are far from your phase center, which are now going to be fringing significantly, and an RFI source?
And what are the tools? Is that a problem? Are there other handles that you're using? Is that, are they well separated anyway? Because you're assuming you have moving sources, or?
Yeah, so I believe that they will be separated because we're doing a antenna-based decomposition. And it's also contributing a very small amount when it's, very far from the field center. Admittedly, I'd love to talk more about this for things like MWA, which are much greater field of view than what I've been thinking about. But I believe because you're jointly estimating for all of the baselines, that you can then get separation between a sidereal and non-sidereal source, because you're not just independently working on each individual baseline. So you've got all that combined information. So that would be the best answer for that, I think, for now. Yes, Stephen.
Yeah. Can I jump in on? Yeah, yes. This last line there mentions that we're sort of working together on some EoR2 data. That's the ultimate field. That's the entire scope.
Yeah.
So when we're looking at these sorts of signals with the MWA or with EoR2, what we find really useful is differencing, because these satellites and planes are moving signals. You can difference time step to time step, or frequency channel to frequency channel, or LST to LST, to remove all of those astronomical objects and just isolate the signal from the moving object, either a plane or satellite. So as we hopefully work together a bit more on that last thing, there are the sorts of things that I'd like to look at. Is looking at the difference visibilities, where all the universe goes away, you can isolate the signal that way. It's pretty cool.
Yeah. So just to repeat for those online, Stephen made the comment that with differencing of the visibilities, whether it's between time steps or frequency channels, we should be able to isolate the RFI sources from the astronomical sources, which are staying constant from one time to another.
Okay, so thanks.
Thank you very much.
Don't see any online questions, so since we are just out of time. So thanks everyone. Thanks Chris, and also all other speakers this morning. And sorry about running a bit late and cutting into the lunch time, but I suggest that we still come back here at scheduled time. It's 1:30 local time, or 50 minutes from now. Any announcements, important announcements, Venus, Stephanie? Okay, all right, so we see you in about 50 minutes.
I don't know. Yes, I'll leave that.
Sure. Okay, thank you.